All right, hello, good morning. Sorry I'm not able to be with you there in person today, but let's continue our journey through Chapter 11 nonetheless. So in class, we spent a lot of time motivating the need for ideal solutions, right? So the topic of Chapter 11 is ideal solutions. And how we keep motivated in class is we're trying to define a new, reference state or standard state that we'll use to define ideality in liquid phase solutions. Okay, so here we go. In this screencast, we're going to start to talk about property changes upon mixing. We'll work out our partial molar properties of an ideal solution. We'll end this video, and then we'll move on to fugacity and ideal solutions. We'll stop that video. Then we'll get into Rayold's law, and we'll start to solve a bunch of problems using Rayold's law. So when it comes to property changes upon mixing in an ideal solution, so first, remember when we talk about mixing, conceptually it's, I have, say, a beaker of pure component 1 at a given temperature and pressure, a beaker of pure component 2 at the same temperature and pressure, and I'm mixing them to form a solution at the same temperature and pressure. Right? So I'm mixing at the same temperature and pressure. For the case of an ideal gas, we're able to derive our property changes upon mixing. We're not going to do so here for an ideal solution. Okay, but the key important result is that the property changes upon mixing of an ideal solution are equivalent to that of an ideal gas. So the property changes upon mixing of an ideal gas and ideal solution are the same. We derive them for the case of an ideal gas. We're not going to derive them for an ideal solution because it's beyond the scope of this class. Okay, but intuitively, they should make sense. Remember, an ideal gas is a system in which molecules don't interact and they don't take up space. Now, an ideal solution is going to be a system in which molecules interact, but all of those intermolecular interactions are going to be exactly the same. So if I have a mixture of A and B molecules, right, A is interacting with A, B is interacting with B, the same as A is interacting with B, right? So AA, BB, and AB interactions are all going to be equivalent. So we have interactions, it's just all of our interactions are exactly the same. So in terms of property changes upon mixing, my property changes upon mixing are exactly the same as that of an ideal gas. So if I start with, say, delta H of mixing, okay, so delta H of mixing in an ideal solution is just equal to 0, right? And intuitively, okay, if I have an ideal solution and all of my molecules are interacting in exactly the same way, okay, intuitively it makes sense then that delta H of mixing is going to be 0, right? That I have an athermal solution, right? Likewise, so that's delta H, okay, but delta U of mixing of an ideal solution is also going to be 0, just like that of an ideal gas, and delta V of mixing of my ideal solution is also going to be equal to 0. So again, ideal solution, I have molecules that interact, but all of the interactions are exactly the same. Right, so the interactions of A with B in an AB mixture is the same as A with A in pure A, the same as B with B in pure B. Right, so intuitively then if I mix them, right, they're still interacting with those other molecules exactly the same as they did in their pure component state. Right, so intuitively, right, it makes sense. Right, I buy it, right? Delta H of mixing, delta U of mixing, delta V of mixing are 0, which was equivalent to the case of an ideal gas. Okay, in the case of an ideal gas, we derive that using the Gibbs theorem. Right? We're not going to do so here for ideal solutions. It's beyond the scope of this class. All right, then that gets us to delta S of mixing. Okay, so remember delta S of mixing. Okay, so when I talk about delta S of mixing and delta G of mixing, okay. Now I said, okay, when I think about property changes upon mixing, I have a beaker of pure A at a given temperature and pressure, a beaker of pure component B at the same temperature and pressure, and I'm mixing them to form a final solution also at the same temperature and pressure. Okay. The other thing I'll add when I talk about delta S and delta G is when I mix, I'm mixing to form a single homogeneous phase. Okay. So when I mix pure A and pure B, I mix to form a single liquid phase. There's no liquid-liquid equilibrium happening right in that final mixture. Okay, that's a topic for chapter 13. If I have phase splitting, well then I'm actually going to get a delta G of mixing greater than 0, but don't worry about that here. So when I'm mixing, when I'm talking about my property changes upon mixing, I'm mixing to form a single phase. Alright, so in terms of delta S of mixing, okay, remember delta S of mixing is always going to be positive. It's always going to be greater than 0. And what I've told you in class is The key thing to remember is sum over I, xi log xi. Okay, I think with ideal gases we used y. Here I'm going to use x for mole fractions. So key is sum over I, xi log xi. So xi is my mole fraction of component I. That's always going to be less than 1. So log xi is always going to be negative. Okay. Well, delta S of mixing always has to be positive, right? So therefore I have a negative sign in front to change my sign. And then it's going to be a negative R. Okay, remember R has the same units as S, right? Joules per mole Kelvin, right? So it's negative R sum over I xi log xi. All right, now in terms of delta G of mixing of my ideal solution, okay, again, remember what's key is remembering sum over I xi log xi. Okay, again, xi is always going to be less than 1. Log xi is going to be negative. So I'm going to need a positive sign here, right? Delta G of mixing is always going to be, so for an ideal gas or ideal solution, it's going to be less than 0. Okay? So I need a positive sign here, right? So that this is negative, and then this is an RT, right? So delta G of mixing, okay, is always going to be less than or equal to 0, right? For my ideal solution here, in an ideal gas, it's always going to be less than 0, right? Xi is less than 1, log xi is negative, so I have a positive sign here, and RT has the same units as G. Okay? So there's my property changes upon mixing of an ideal solution. Great. Now, how do I use those? Is, well, remember in general, we had that, my property change upon mixing, right? So I'm going to say delta F of mixing is equal to the actual value, right? And I'm going to write functional dependencies the first time I do this. So delta F of mixing, which is a function of temperature, pressure, and composition. Remember, F is any arbitrary thermodynamic state function, so HU, V, SG. So delta S of mixing at my temperature, pressure, and composition of my final solution is equal to the molar F of my final mixture minus, then I'm going to have the molar average of their pure component F's, right, of those two components, or those components that I mixed to form my final solution. Okay, so just reminding myself that this is my pure component, okay, and this is my final state of interest. Okay, and so how I could use that is, one, if I wanted to calculate F, right, and so then F at a given temperature, pressure, and composition is equal to, so bring that over, molar average of my pure component F's, okay, plus delta F of mixing. Okay. So first then, if I think about an ideal solution, okay, that would give me that H, okay, of an ideal solution. Okay, I'm going to write down functional dependencies here just to make sure I'm clear, since I'm not there in person to directly answer your questions, right? So this tells me then the enthalpy of an ideal solution is just equal to the molar average of the pure component enthalpy of the two components, or the components that I mix to form that final solution, because delta F of mixing is 0. Okay. Likewise, delta U, not delta U of mixing, U of my ideal solution is just equal to the molar average U V of an ideal solution, okay, is just equal to molar V, okay, and these will become important in chapter 12 when we define excess properties. Okay. All right, so that's H, U, and V. Okay, my entropy of an ideal solution, okay, at TP and XI, okay, it's going to be molar average plus delta S of mixing, which we'll put in, so XI SI at T and P plus delta S of mixing. Remember that was a minus R sum over I XI log XI, and then G H minus TS, or sum over I XI GI at T and P minus or plus RT sum over I XI log XI. Okay, so we have our property changes upon mixing for an ideal solution. All right, now we have expressions for enthalpy, internal energy, volume, entropy, and Gibbs free energy of an ideal solution. Okay, these are going to come into play in chapter 12, where we'll define an excess property as actual relative to ideal solution. So we'll need these. And then next I want to get partial molar properties. And we can get partial molar properties a number of ways. Okay, the easiest way I typically find is just by what I quote unquote and say matching. So in terms of partial molar properties, what I mean by that is, if I think about my arbitrary property change upon mixing again, right? Delta F of mixing. Okay. So if I go back to my expression, right, and I'm going to just drop my functional dependencies for compactness, and we'll put them back in. So delta F of mixing, we said was equal to F minus sum over I, xi, fi. Remember, an expression that I like using is, well, F I could equivalently write as sum over I, xi, f bar I, and then that's still minus sum over I, xi, fi. So grouping terms, all right, we had delta F of mixing, okay, and I'll write this as that Tp and xi is equal to sum over I, xi times f bar I at Tp and xi minus fi at T and P. Right? And see, try and squeeze in the last parentheses, right? And, I've always mentioned this one in class. I like this, right, because my partial molar property, that's like my effective value in solution. Here's my pure component value. So my property change upon mixing is the molar average of the difference of my partial molar, right, and molar property at the same temperature and pressure, right? So it kind of, this gives me a deviations, right, from that pure component value. All right. So if I think about this matching then, well then let's look at H, right? So if I look at, say, delta H of mixing, okay, of an ideal solution, okay, that's equal to 0, okay? And my property change upon mixing for an ideal solution must be consistent with the general case, right? So that's going to be equivalent to sum over I, xi times f bar I minus fi. So in order for this to be true in general, and actually I've got to put h's in here, right? So in order for this to be true in general, it must be that h bar I, okay, which is at Tp and xi, is equal to hi at T and P. Okay, I should put ideal solution on here, right? So this is the partial molar enthalpy in my ideal solution. That's just my pure component value, right? So I need not label it. So we find that the partial molar enthalpy of component I in an ideal solution is just equal to its pure component value at the same temperature and pressure, right? Cool. All right, looks like the result from an ideal gas, okay? But, again, in an ideal solution, we have a system in which our molecules are interacting, but all of those interactions are exactly the same. So when I have a system of pure component A, right, all those molecules are interacting in exactly the same. I have just AA interactions, and all of them are the same. When I put in a solution with B, right, still all of the interactions are exactly the same, right? And so, it makes sense that the enthalpy, or the partial molar enthalpy of component I in that mixture, right, the effective enthalpy of component I in that mixture is the same as its pure component value at the same temperature and pressure, right? I'm at the same temperature and pressure. All of the interactions, or my interactions with everything else, are still exactly the same, right? Okay, I buy it. Okay, and we could do the same thing. So delta U or partial molar volume, partial molar internal energy are all exactly the same. I'm just going to write them down for compactness, because the key is delta V of mixing of an ideal solution is also equal to 0. Delta U of mixing of an ideal solution is also equal to 0. So we get to the partial molar volume of component I in my ideal solution at Tp and xi is just equal to the pure component value at T and P, and then we get that the partial molar internal energy of an ideal solution, right, is also equal to its pure component value at T and P. Right? And in case I didn't mention in class, right, so an ideal solution, right, we have this mixture in which all our interactions are exactly the same. So just to be clear, right, a pure component state is an ideal solution. Right? So if I have pure component, just pure A, well, it's an ideal solution, right, in that context, and that all of the interactions are exactly the same. And so when I have a mixture, okay, so before I sidetrack and look at G, right, so when I look at, my mixture, okay, if I know we love limits in class, right, if I were to look at the limit and say xi goes to 1, right, in pure component limit, so let's say the limit as x1 goes to 1, H ideal, right, is just equal to H1, right? In my pure component limits, right, I just have my pure component enthalpy, right? And, pure solution is an ideal solution, right? So all solutions, right, even when they're non-ideal, are going to obey ideal solution properties in that pure component limit. So when I look at my expressions, right, this was even on your last exam. Okay, so here I have H ideal. If it was just H in general, I know that my pure component limit is just equal to the pure component enthalpy of that component. Okay, and when it comes to ideal solutions, right, one thing to think of or to remember is that a pure solution is an ideal solution. And where we'll use this also in, say, chapter 12, is remembering that all solutions approach ideal solution behavior in the pure component limit. Okay, but I diverge as always. Okay, but all right, so let's get back to partial molar properties. Let's get entropy next. Okay, so again, the key is that, okay, delta S of mixing, okay, of my ideal solution. Okay, well, we said delta S of mixing, that's going to be also, even if I can't remember, what I remember is sum over I, xi, log xi. Then I need a negative sign, because this is going to be positive, and log xi is always negative, right? Xi is less than 1. So negative r, sum over I, xi, log xi, and that has to be equal to, or consistent with, sum over I, s bar I of an ideal solution minus si. Okay. Cool. So I'm going to do a little more work in terms of matching. So in terms of, and I forgot my xi in here. Sum over I, xi, s bar I minus si. So in terms of matching, I'm going to do a little bit more work in that negative r is just a constant, so I can bring it into my sum. All right, I could think if I had this long sum of negative r, xi, log xi terms, right, I could factor out that common term of negative r, which is what's done here. So this, right, is equivalent to sum over I, xi times negative r log xi, and that has to be equal to sum over I, xi, s bar I ideal minus si, and these two must be consistent, so it must be that s bar I ideal minus si is equal to minus r log xi. Therefore, s bar I of my ideal solution at a given temperature, pressure, and composition is equal to my pure component value at T and P minus r log xi. Okay. Remember, when we talked about entropy in an ideal gas, right? An ideal solution is the same in that, so I have this mixture, right? I have pure A and pure B, and I mix them to form a solution, which all the interactions are exactly the same, right? So, delta H of mixing is 0. So the reason or the rationale for delta S of mixing being positive is it's purely combinatorial. The idea is I have, A molecules and B molecules, right? So if I'm in a mixture of pure A and I swap the position of two A molecules, well, the system's still exactly the same, right? Those molecules are indistinguishable. So even if I took two A molecules and I switched their positions, nothing's changed. When I look at my pure B solution, it's the same thing, right? The molecules are indistinguishable from each other. So if I switch B with another B molecule, nothing's changed. Now when I get in my mixture and I have A and B molecules in solution, now those A molecules are distinguishable from my B molecules. Okay? So if I were to take an A molecule and I were to switch its position with the B molecule, I have a new unique configuration in my system. So it's purely combinatorial in that when I take my mixture of A and B molecules, or when I create this mixture, there's more unique configurations available to my system, right? So the positive delta S of mixing is because the number of states available to my system has increased. Okay, cool. And remember, delta S of mixing is positive. That's why separation processes are so hard, because I'm taking a mixture and I'm trying to separate it into, say, two streams, which are more pure, right, in my, say, most volatile and least volatile component if it's VLE. Okay. Well, so that means I'm going to have to actually, decrease my entropy. I'm going in the opposite direction as nature wants. If it's distillation, I've got to put energy in then to drive that separation. Okay. All right, so that was delta S of mixing. Okay, now key is, so partial molar S. So this is my partial molar entropy of my ideal solution. It's equal to my pure component value at T and P minus R log Xi. So again, Xi is less than 1. Log Xi is negative. A negative of a negative, this is positive, right? So my partial molar entropy of component I in an ideal solution is greater than its pure component value at the same T and P, right? So mixing increases my entropy. Okay. And again, ideal solution, ideal gas, it's purely combinatorial. Okay. Yeah. All right. And actually, so the smaller the value, so if I have an R or an Xi of approximately 1, right? So in the limit that I approach 1, the pure component limit, this is just 0. But then as Xi decreases, okay, this is going to be more and more positive. Okay, so the partial molar entropy becomes larger and larger relative to that pure component value. Right? And it's just, hey, more states are going to become available to that system in the mixture. Now let's get G. Okay, so the last one is G. And so we have the delta G of mixing in my ideal solution is equal to, so key is sum over I, Xi log Xi. Okay, log Xi is going to be negative. Okay, delta G of mixing is always negative. Okay, or less than or equal to 0. It's going to be less than 0 for an ideal solution and ideal gas. So I'm going to have a positive sign to make sure that's always negative, and then multiply by RT. RT has the same units as G. Okay, and that must be consistent with our general definition, and so that's going to be sum over I, Xi, and write G bar I, ideal solution, minus GI. Okay. All right, so then just like entropy, right, my match, right, RT is constant. I'm mixing a constant temperature and pressure, so I could bring this into the sum. So this is equivalent to sum over I, Xi times RT log Xi, and that needs to be equivalent to sum over I, Xi, G bar I, ideal, minus GI. Okay, and so matching then, and then I'm going to get G bar I ideal minus GI is equal to RT log Xi. Okay, so G bar I ideal at TP and Xi is equal to GI, my pure component value at T and P, plus RT log Xi. Okay, and one final comment, right, is G bar I ideal. That's my partial molar enthalpy, right? That's equivalent to chemical potential. So I could equivalently say the chemical potential of component I in my ideal solution is equal to GI at T and P plus RT log Xi. Okay. So when it comes to partial molar Gibbs free energy, okay, Xi is less than 1. This term is going to be negative. My partial molar Gibbs free energy of component I in my ideal solution is less than my pure component value. Right? It's thermodynamically favorable for that component to be in my mixture relative to, right, the pure component state. All right, so there's my partial molar properties, property changes upon mixing, properties of my ideal solution. Right? Life is good. So I'll stop recording this video, and then I'll start recording another one in which we talk about now fugacity in my mixture, and then that'll lead it to Rail's law, and then we'll solve a whole slew of Rail's law problems. All right, we'll see you in a minute or two.